welcome everybody once again. Next, we have the final third lecture of Héctor.
So, well, thank you very much for the introduction, and also thanks to everyone for being here for the last day of this series of of this mini course. So today there will not be a practical session. We will only have a 1 hour talk, and I thought of this a bit of an example of the things that can be done with the tools that we reviewed in the previous 2 days. So the topic on which I work mostly is on simulating the appearance of black hole mimickers to the Event Horizon Telescope. So this presentation will be a review on, or some kind of biased review on this topic. That may be a bit inclined towards a bit more the things that I do. So, I hope it is interesting for you as an example of the things that can be done with these tools. So, what happens at the edge of black holes is probably one of the deepest questions currently in not only in astrophysics but in physics in general. Astronomers normally, when modeling black holes, assume the Kerr hypothesis. The Kerr hypothesis, one can say that it is the assumption that the Kerr solution in general relativity, complete with an event horizon, accurately describes astrophysical black hole candidates. However, if we ask other people, there are several researchers working on quantum gravity and extensions to GR that would say that this description should break down at event horizon scales, where new pieces could emerge. Now, however, the only way to decide things in science is by looking at observational evidence. For the first time in history, we are being able to probe the strongest gravity regime. During the last decades, there were 2 very important breakthroughs. One of them was the first detection of gravitational waves, and the other one was the possibility to look at the event horizon scales with electromagnetic observations, thanks to the technique of very long baseline interferometry. So this is just the beginning. The next experiments that will come during the next decades, so both the next generation of gravitational waves and the next generation of the Event Horizon Telescope, together with probably space-based observing stations, will allow for unprecedented accuracy in the next observations. The 2 observing techniques are actually complementary. While gravitational waves observe mostly systems that are highly dynamical and currently at the stellar mass scales, later probably we will be able to also see supermassive scales. So while this is the focus of gravitational wave experiments, the focus of VLBI observations is more on quasi-stationary systems that are currently on the supermassive range. And that's actually the only thing that we can observe so far. Systems that are almost static, they don't emit gravitational waves, and objects have to be big enough in order for us to resolve them. So in this, you will hear a lot about gravitational waves, and in the talk by Ulrich this afternoon, which I look very much forward to hear. And here in this talk, I will focus instead on the appearance of black hole alternatives in the electromagnetic channel, and especially for the case of very long baseline interferometry experiments. So, as we already discussed in the previous talks, the way in which the interpretation of observations is made in the Event Horizon Telescope, which is currently the largest VLBI experiment, goes more or less in this sequence. So we start with a space-time model. We use this as a background to perform general relativistic magnetohydrodynamic simulations, or GRMHD simulations, that simulate the behavior of the plasma. Then on top of this, we can decouple the behavior of radiation and simulate the well, how radiation is emitted and how it gets transported through the plasma using general relativistic radiative transfer simulations or GRRT simulations. And finally, we incorporate the observational uncertainties associated to the observing conditions and to the instruments. This pipeline was used, for example, in the well, in the recent series of papers for Sagittarius A star, trying to test the black hole metric. So an example of where simulations played a very important role was in calculating what is called the alpha calibration. So theoretically, we can expect what should be the shadow of a black hole just by calculating the impact parameter. However, if we take images of simulations and try to analyze them, actually the shadow is something that is hard to define and hard to measure. It is better or less ambiguous to measure the size of the bright ring that we observe. For the case of the actual observations, it is exactly the same. So we have the first null in visibility amplitude that I showed you yesterday, and this gives the diameter of the ring, but this is the diameter of the bright ring, not of the shadow. So the way simulations play an important role here is that we can perform a lot of these simulations and see what is the size of the shadow that corresponds to the size of the ring that we can measure. And this is this alpha parameter that appears here. So now this links the observed diameter of the ring with the predicted diameter of the shadow for that space-time model. And then we can use this to parameterize deviations with respect to the size of the ring that we should observe or that we would expect, for example, from the Schwarzschild metric. So, well, using this parameterization and this calibration, it was possible to compare the observational results and use the independent mass measurements for Sagittarius A star in order to constrain and even rule out parameter ranges for several ways in which deviations from Kerr could happen. So, well, however, in that same paper of the EHT collaboration, it was paper 6 of the series on Sagittarius A star, not only alternatives to Kerr were considered, but also some more radical hypotheses. So it could be that what we are looking is not only a different type of black hole from Kerr, but it could be that it is not even a black hole. No? It could be that it's an object that doesn't have a horizon. And there are many of these objects that have been considered in the literature. However, still, even though this possibility was considered in the EHT papers, there is still a lot of room to improve. So that there are many things that we can still do. Most of the cases that were considered there are semi-analytic approximations or use several simplifying assumptions. So this is a critical blind spot, because if most of our models consist of Kerr black holes, we may be undersampling other possibilities, and we may be less sensitive to important physical discoveries. So, indeed, this was already something that was noticed by the community even beforehand, and there has been a lot of activity on simulating the appearance of these alternatives to black holes. So currently this is a rapidly evolving field. If you are interested to know more about this, there is a review on simulations on exotic compact objects that was authored by myself together with Prashanko Cherlakota and Carlos Cerdeiro, that was published last year. And there is also some notes from a conference dedicated to black hole mimickers that was held also in 2025 that contains a previous version of this talk, because many things have happened in the meantime. So, Well, then let's go back to these exotic compact objects. So several of these hypothetical objects that have been proposed in the literature are expected to share some observational properties with black holes, and this subset of models is what can be called black hole mimickers. But where should we expect them to exist? So some of them have been proposed to solve problems associated to the event horizons, as I mentioned in the first slide. So there are several researchers that consider that event horizons are too problematic, for example, for issues such as the information paradox, and they shouldn't exist at all. So this is the case, for example, for proposals such as gravity star, false balls, black shells, and other. However, this is not the only way, the only reason why we may expect that there is something different from black holes. There are also other objects that appear as predictions from general relativity under very specific circumstances, or for very particular types of matter. This is the case, for example, for some naked singularities, for bosonic stars, and for wormholes that we will discuss later. And finally, many extensions to GR contain their own version of these types of objects. So there are many channels from which we may expect these black hole mimickers to exist. But more important than what is the motivation for them to exist, from the point of view of observations, is what should we actually observe if these objects were there. So instead of classifying them because of their motivation, in the next slides, or in the rest of the talk, I will address several of these objects from the point of view of how they interact with the environment, which is what will ultimately determine their observational properties. And here, because the general scenarios are very difficult to treat, I will consider two extreme cases. The first one would be when there are significant non-gravitational interactions. So if these objects interact with matter by means different than gravity, and these interactions are strong enough that they can scatter matter or radiation, this scattering will lead to the formation of effective surfaces. So because it is a bit similar to when we look at the sun, for example. So the sun has some particular optical depth, and then that is given by the interaction of the mass that makes up the sun with light. So light gets scattered, and we can define some depth that we can link to an effective surface. The other extreme scenario is the opposite case, where we have negligible non-gravitational interactions. In this case, matter that approaches the object is free to explore all of its interior spacetime that can contain several particular features, such as regions of extreme curvature that we may call naked singularities, wormhole throats, or even just regular interiors that here they seem to be the most boring alternative, but I show you later that they can actually have very interesting possibilities. So let's start then by the first case. Let's first consider surfaces. So one of the easiest thing that can be considered first is a thermalizing surface. So in that case, we replace the event horizon by a surface that is located slightly away from what would be the would-be horizon. And this slightly away, we parameterize it by this dimensionless parameter mu. So there is an old argument that was made by Broderick and Aragon from 2006 that considers that if one accepts a set of three minimal assumptions, one can predict and rule out to some extent the existence of a thermalizing surface around a black hole candidate. These minimal assumptions are just these three: energy conservation. We also ask that the effective surface respects the laws of thermodynamics, so that if it is coupled to all electromagnetic modes in radiation, so that if it is heated, it will radiate as a black body. Then we know that astrophysical black hole candidates are accretive. This means that matter that comes from far away will reach this effective surface and will need to stop. So when it halts at this effective surface, it will emit some of the energy that it has, or actually it will transfer this energy to the surface. The surface will heat, and then we should expect to perceive some radiation from this surface. This is something that it is relatively easy to calculate. So one can expect that the efficiency at which radiation is converted, at which kinetic energy of the accreted matter is converted to heat that will heat up the surface is given by this expression. So in general, it is inversely proportional to the radius where the effective surface is located. So the closest to the would-be horizon, the harder the matter will hit the surface, and the more the surface will be hit. So, plainly from these assumptions, it is then possible to calculate, given the estimated mass accretion rate of Sagittarius A star, where in the spectrum we should see this the emission associated to this surface. In fact, this will result in a peak that will be located more or less in the infrared, and the precise location of this black body spectrum would be given by the size of the effective radius of this surface. Fortunately, now that we have the HT observations, we can put an upper limit on this. So we cannot make this surface arbitrarily large. And this is important because then we cannot move this black body spectrum arbitrarily here. It is constrained to be in a particular region, and because we don't see this this thermal bump in the infrared, we can safely conclude that we are not looking at a thermalizing surface. So this is the basic version of the argument, but it is still possible to complicate it in some ways in order to still allow surfaces to some extent. So one argument that has been put forward is that it is possible that because of the extreme redshift close to the would-be horizon, even if the object thermalizes, it will take for us a long time to see the time when it thermalizes. So radiation will, from the time that it thermalizes, will take a lot of time to reach us. So this argument was put forward by Lu in 2017 and allows to put an upper bound on what would be the size of this thermalizing surface. So this new parameter then should be something smaller than 10 to the minus 14. That is what corresponds to the time that it would take us to see the thermalization of the surface in the lifetime of Sagittarius A star, or in what we estimate as this lifetime. And finally, there is another bound that in this case this is a lower bound that is provided by an argument related to causality that was put forward by Carballo Rubio in 2018. So this argument states that if we want this object to stay a non-black hole, so to not have a horizon, we need to make it expand in a time that where that is compatible with the speed of light. So because matter is accreting continuously, so the mass of this object is increasing, and if it doesn't expand, it will become a black hole. But we also want this expansion to be subluminal. So based on that argument, it is possible to put a lower bound on this new parameter. Translated to the radius of Sagittarius A star, this gives bounds that are in centimeters and go from 10 to the minus 11 to 10 to the minus 2 centimeters. So currently, these are the bounds on where a thermalizing surface is still allowed for Sagittarius A star. And very interestingly, this lower bound excludes surfaces that are located at a Planck length away from the would-be horizon. That is an argument that is put forward very often in string theory models. So, well, however, this is one way to get around of the argument and to reply to that to those caveats. But this is not the only way of doing that. So other proposals to get around this idea of the thermalizing surface are by considering that this matter that makes up the surface has some exotic properties. Some possibilities that have been considered are that these objects possess extremely large heat capacities. That is something that has been mentioned for gravastars, for example, or that they are consisting of electromagnetically inactive matter. That is something that has been put forward for black shells, or that they radiate only in a few bands. So, but however, even in such case, the argument should apply still to the layer of normal matter that gets piled up from accretion. And in fact, a surface density of even 1 gram per square centimeter is enough to make the material optically thick. And then these arguments should still apply to that layer of normal matter. So, well, however, for the sake of completeness, we can get away with this argument, maybe assuming that also something that is mentioned several times in the string theory community, that this matter that reaches this surface gets converted immediately to this form of exotic matter that is electromagnetically inactive. So let's consider that we allow for this. Even in this case, there are some things that we can say about the reflective properties of the surface. So let's consider now that this surface doesn't thermalize, but it has some reflectivity that we can measure. And let's consider that it is responding at the observing frequencies of the EHT. So there are some works that have considered this possibility. So in 2022, Carvalho Rubio considered this using semi-analytic Keplerian mixed models. Then in paper 6 of the EHT that I mentioned before, this was considered for non-rotating reflecting surfaces using a DRMT simulation. That is the plots that you can see here. And in a work from 2024, led by Jules de Klever from Nijmegen, we generalized these considerations for the case of rotating surfaces, which is what you can see in the image that is here. So in this case, you still see a dark region that corresponds to to parts where the surface is not reflecting the accretion disk. But one also can see a series of concentric rings that are reflections from the accretion disk. By varying the albedo of the surface, so it is possible to put constraints on what the albedo of this hypothetical surface should be. And currently, these constraints place it below 0.3. So this is already interesting because it allows us to put a limit on the physical properties of this surface. But also, if one compares it with other known objects, we can see that actually the constraint is not. There are a lot of things that are still allowed within this constraint. For example, if we look at the albedo of the moon in the invisible wavelengths, this is already something that would be still allowed given this constraint. Even though this is in radio and this is in optical. So, well, these are the current constraints given by DHT on naked singularity. On reflecting surfaces. Now let's go to the next exotic object. Now we are just considering gravitational interactions, and this next possibility are naked singularities. So naked singularities express our ignorance about the theory of gravitation. So we don't expect that something like a mathematical singularity exists in the universe, but they are just a placeholder for the neighborhood of a point described by a yet unknown theory of quantum gravity. And for simulation purposes, what we do is that we excise the singularity and replace it by a boundary condition that can be reflecting or absorbing. There are already simulations in pure hydrodynamics of the naked singularities. For example, Cosimo Bambi did in 2009 some simulations of accretion onto Kerr superspinors. And there is also this more recent work by Krajewski and Gluznia. But the first simulations of GRMHD accretion onto naked singularities in the style or following a pipeline similar to that of EHD observations were performed by Indu, Dihingia, and collaborators in 2024. This was for Kerr superspinors, and then the same team has considered other cases of naked singularities. There are also some simulations from this year that consider a very interesting type of singularity that is the JMN1 singularity. Here you can see some examples from the first paper by the Dihingia collaborators. This is a black hole. This is the image of a Kerr superspinor. And you can see that, very interestingly, both of them produce also central brightness depression, even though in this case, this simulation shows some additional rings inside. So while this tells us that in principle we can distinguish a Kerr black hole from a Kerr superspinor, what I found most interesting about these images is that naked singularities can produce shadow. And they produce shadows by exactly the same mechanism of black holes, that is by capturing light. So they also have an effective cross-section for photons, and they produce shadows in exactly the same standard way. So, a particular case of naked singularities that I am currently considering together with some collaborators are naked singularities that come from quadratic gravity. So quadratic gravity is a theory that is very interesting theoretically because it can be perturbatively renormalizable, and it is said to be a prototypical zero of quantum gravity. Solutions in this theory include the Schwarzschild solution, but more generally they are or can be naked singularities and wormholes. In fact, some collaborators characterize all the possible solutions that you can get in this theory. And interestingly, there are 4 qualitatively different cases of naked singularities that behave very differently if one looks at their effective potential. These include cases of singularities that are attractive and repulsive. So we simulated accretion onto this type of singularities. And very interestingly, we found that matter tends to accumulate and heat inside of the would-be horizon. So even though these objects don't possess a surface in the same way as the cases that we considered at the beginning, the fact that matter piles up here and heats and gets optically thick means that actually we can constrain them in the same way as we were trying to constrain thermalizing surfaces. And in fact, if we try to calculate a spectrum from this, we see that also in this case we would have a thermal spectrum peaking near the infrared, while the observations of Sagittarius A-star spectrum don't seem to favor this. So some models can be ruled out currently and so far by similar arguments as for thermalizing surfaces. So, well, let's now consider some different possibilities. Let's now consider the case of wormholes. So, well, wormholes are very interesting. I think they are some of the most interesting hypothetical objects out there. And also, well, from the point of view of their optical properties, they exhibit a very rich phenomenology. So you can have features such as multiple rings. One can have views of the other universe and even reflections from our own universe. And all of this is really nice, but the natural question is, does this survive in a realistic accretion scenario? One needs to perform simulations, of course, in order to find out the answer to this. And unfortunately, currently, we equal to no? The answer is that probably not. So in 2004, Luciano Combi performed some GRLD simulations of accretion onto a Simpson-Fisher wormhole. The outcome of these simulations is that matter seems to accumulate in the throat, forming a hot and dense spherical structure. So this happens, and it is something that will possibly happen for other case wormholes, because the throat is an extreme. In this case, it is a minimum. Something that is yet to be seen is whether other solutions could turn it into a maximum or a saddle point. But well, so far these simulations point to the prediction that if we look at this in images, we will see something like a bright sphere, and therefore incompatible with what we see in observations of the HT. So one may think that this is just because the object doesn't have a sink where matter and radiation can disappear, which is something that we have, for example, in the case of black holes or in the case of the naked singularity. But actually, and well, very interestingly, I will show you in the next slide that well, having a sink is not the only case in which one can have images that are that produce a central brightness depression. And in fact, one can produce central brightness depressions for objects, not only that they don't have a sink, but also that they don't have that they are not extremely compact and that they don't have an extreme redshift. So, and this brings us to the case of exotic stars. So we are still analyzing the case of negligible non-gravitational interactions. So we may consider that these objects are made of dark matter. And this is not a very ad hoc assumption, because actually some of these stars appear motivated not as a replacement of black holes, but predicted by the existence of extra bosonic fields that could be dark matter candidates. But from the practical point of view, this results in that again, accreted matter can explore the interior, even if the solution is a non-vacuum solution. So you have probably already heard more about that in the talk by Carlos on Monday. But well, just for completeness, I can mention that these type of stars contain as a subset the family of boson and Broca stars, and that they don't exclude black holes because they were not motivated as a replacement of them, but they can actually coexist with them. So some of the members of the family, in fact, have only moderate redshift, as I mentioned before, and they don't be compact enough to possess light rings. The literature on the observational properties of these objects is abundant. So there are papers predicting, for example, spectra of Shakura-Sunjaev type disks since 2009 by Francisco Guzman. But here I would like to focus on a particular work that is that of Vincent from 2016. In this work, the team simulated images of tori around boson stars. And well, as you can tell from this comparison that has the boson stars present here and a curved black hole here, actually one can get images that are very similar, and that probably for a resolution like that of DHT could make a boson star pass by a black hole. However, there is some trick in these images. For the case of boson stars, what we see is not actually a shadow, but is more a lens image of the hole that is in the center of the torus, of the hole in the donut. And then the size of this hole is not something that is given by the model itself, but is instead something that is chosen a bit arbitrarily in order to highlight the possibility that there is this degeneracy. So a natural question is whether we can make predictions on what would be the size of this hollow in a realistic setting, and also if we can use numerical simulations to find it. So the answer of this is yes, But before going on and showing this to you, I would like to take a bit step back and recall some things on accretion disk theory. So in the first lecture of this series, on Tuesday, we were discussing the magnetorotational instability, which plays a crucial role in angular momentum transport in hot accretion flows. So then it is natural to expect that if we want to find what would be the inner edge of an accretion disk, this inner edge could be provided by suppressing the main mechanism that allows accretion. So if we stop that main mechanism that allows accretion, then matter will not go further and it will stall at some radius. So we saw on Tuesday that a necessary condition for this instability is that we have a profile of circular geodesics, of a rotation profile, not necessarily geodesics because this is hydrodynamics, but we need a rotation profile that is decreasing with radius. This is a condition that is generally well fulfilled in astrophysics because that is precisely the case for Euclidean accretion disks, and this is also the case for equatorial geodesics in the Kerr spacetime. But by looking at what is in general the rotation profile of geodesics, or even in Newtonian dynamics, by looking at Kepler's third law, we can see that it is also very easy to violate. So if we have a mass function that increases faster than r to the cube, and r to the cube is what it should increase in the case of constant density. So if we have an object with density that increases faster than constant density, then this requirement will be violated and the magnetorotational instability will be suppressed. So, so we see that this will be very easily violated if we have a spacetime that is non-vacuum, and that is precisely the case for bosonic stars. So in a work from 2020, we use the code that we have been learning in the first session in order to simulate accretion onto two different boson stars models. One of them had a maximum of the rotation profile, and the other didn't have it. So you can see here the simulations in the meridional plane for a black hole, the boson star that had the maximum, that was model A, and the boson star that didn't have it. And we can see that the case that had the maximum produces precisely this accumulation of matter away from the origin, while the origin and this region inside that radius stays more or less empty. Then, if we retrace these simulations, we can see that actually, in fact, boson star model A produces an image that has a central brightness depression, while boson star model B produces an image that is just a glowing ball. However, if we compare the size of the ring of the central brightness depression of boson star model A with that of black hole, we see that it's significantly smaller, and it is small enough for the EHT to notice this difference. However, well, we can try to make predictions and explore the rest of the parameter in the family of mini boson stars. Unfortunately, we find that unfortunately for this model to be a successful black hole mimicker, we see that all the members of the family will produce central brightness depressions that are smaller than that expected from a Kerr black hole shadow. And not only that, but also all of the models that produce them are on the unstable side of the family. So this is bad news for this precise type of model, but it is actually something very interesting because it gives us a way of predicting where this, what would be the size of the central brightness just by looking at the metric. So this was the motivation for a challenge that was called by Carlos Cerdeiro the imitation game. whose goal is to find a stable model of a horizonless compact object that produces a ring-like image, but is on the stable side of the family. So one candidate that was found a few years ago in 2021 was a proca star that could theoretically produce a ring of size 6M, so quite a big ring. However, well, unfortunately, this particular case was soon later discovered to be unstable. So in the end, it didn't fulfill one of the requirements of the search. However, some more recent study that was led by Víctor Jaramillo and Laura Meneses, then students at UNAM, and also in collaboration with Darío Núñez and Carlos Cerdeiro. So this work scanned the parameter space of another family of boson stars. This is the family known as Q stars. So Q stars are scalar field solitons, and they are characterized by having a sexy potential. So the self-interactions that are in this potential allows to have more stable regions, and even the rotating case that is unstable in the usual mini-boson star seems to be stable for this class of models. So very interestingly, one can have stable cases that have an MRI suppression region that, even if it is not as large as the one that we expect for a black hole shadow, it approaches it, and in principle it seemed to be sufficiently big to be mistaken by a black hole in the observations of the EHT. So let's so of course then this is something that we would like to test with simulations. So we performed GRLT simulations of accretion onto this space-time, and well, very nicely these simulations confirm the prediction. So this is again density in the meridional plane, the equatorial plane, magnetization in the meridional plane and equatorial plane, and we see matter stalling precisely at the radii that was predicted. But now, well, we verify that the effect is present for a case that is stable. And the natural question is now how robust this is. So we verify that it happens, but will it survive? So we ran the simulations for a bit longer than those in 2020, and this is what we found. So this plot shows time on the horizontal axis, and it shows the location of the maximum of density in yellow, and the location of the maximum of synchrotron radiation emissivity in blue. So something that is nice to see is that in general, for a very long time, these maxima are above this is accumulating accordingly to the prediction that was made, which is marked by this dashed line. However, near the end of the simulation, we see that the maximum is displacing towards the origin, and that eventually the maximum coincides with the, well, it gets very close to the origin of the simulation, so that the hole is being filled. So then, well, we ask what can be the mechanism that is driving accretion in this case. So the magnetorotational instability seems to be inactive. We also don't have big noticeable spiral shocks that also transport angular momentum. And because we simulate this in ideal GRHT, we have no viscosity or resistivity. So what can be diffusing angular momentum so that the material gets to fill the center? So one hypothesis was something that could be providing the necessary dissipation of angular momentum would be numerical viscosity. So this is something that one can calculate for a given resolution of the grid. And what you see here, the units that are for the second or horizontal axis of this plot are even in the and probably we cannot. So we can rule out that the effect that is diffusing matter into the central photo is related to numerical viscosity. But what would be then interesting would be to calculate what happens in reality. So numerical viscosity is not something that we have in our universe, no? It's artificial. So, but in our universe we have molecular viscosity. So, in order to provide an upper estimate on what would be the time scale associated to this viscosity, we made some assumptions on the property of the plasma and for example, the density, the mean free path, and we were able to calculate a time scale that would be the time necessary for this type of viscosity to diffuse matter from this region of accumulation until the center, so the origin. For the case of Sagittarius star, the scale that we obtain is in the order of 10 to the 4 years, which is something relatively short in astrophysical times, but the fact that it's much longer than the time that it takes for matter to reach that radius, which is of the order of minutes or 4 hours from neighboring regions, well, favors viewing these radius as a region of accumulation. Furthermore, this scales with the square of the mass of the object, so for MET7 it should be a much longer scale. So in a realistic scenario, molecular viscosity can provide an upper bound. And well, finally, even though we didn't get to ray trace these simulations, the estimated apparent grid size just by calculating the impact parameter as that was associated to this radius is something that is in the order, or actually is something that could in principle fall within the observational uncertainties of the EHT for Sagittarius star. Well, also, I should mention this is not precisely the only thing that what we did. So we calculated this impact parameter, but we also did something a bit similar to the alpha calibration that was mentioned at the beginning. So, well, this concludes the part on just regular objects. So, then we have covered all the cases that I have mentioned at the beginning of the talk. And therefore, the only thing left is the conclusion. So, just to recap, what we discussed today was an incomplete and perhaps a bit biased towards my own line of research revision of the literature on exotic compact objects, focusing on electromagnetic and mainly VLDR observables. We have seen that understanding the astrophysics of exotic compact objects is essential to determine the potential of black hole limiters and also to identify their signatures. We have also seen that interaction with the environment can lead to unexpected phenomenology, and this well highlights the importance of numerical simulation. And finally, the field is developing quickly in the last years, and there is a lot of things to do in case you would like to join. So thank you very much.
Thank you very much, Héctor, for your lecture. And we have questions.
Microfone. Acho que
Thank you, Professor. I think that is in the third slide. When I compare the radius of the shadow, why I compare with the Schwarzschild if I'm expecting some rotation for the solution?
Right. So when the deviation from Schwarzschild, so even if we consider here the deviations are not, and especially so if you start making the black hole rotate, this displaces a bit the shadow, but so this displaces a bit the shadow, but this displacement is not something that changes significantly the radius. So, well, this is one reason, but also, well, for the uncertainty of the HT, the shadow of a rotating black hole would not be significantly different from the shadow of a non-rotating black hole. So, so this is also why we cannot constrain the spin jet with just with shadow measurements. So it is good enough, let's say.
When I have the shadow of the neutron star, why is it so similar to a black hole that has different horizons? I don't understand because they are so similar.
Right. So for the case of the boson star, it is just an apparent similarity. So in both cases we have a dark region in the center of the image, but in the case of the black hole, this is produced by redshift and by the capture of photons. In the case of the boson star, this is more a lens image of the color that is at the center of the accretion disk. So it is not really a shadow because there is nothing that is capturing photons. It doesn't have a capture cross-section of photons, but it is just a region that is dark because there is nothing there. There is nothing there, and it is lens. So in principle, if let's say you have a bright quasar that would be at the other edge emitting ray, you would in principle see that bright quasar in the center of this dark region. So you see dark just because there is nothing there, nothing that is emitting.
I understand the issue of relation of the neutron star also. And this is also similar to
Neutron star? No.
I have wrote the word.
Yes, probably I know what you are referring to.
I say boson for the neutron star.
Sorry, I understood the Boston star, but you mean this sentence, no? Okay, this is not neutron star, this is, I should change this is naked singularity.
Oh, okay. Sorry. The exterior is really similar.
Right, the exterior is very similar, and also the naked singularity does have a capture cross-section. So if you set it to be absorbing, it will capture photons, and as you say, because the exterior is very similar to that of the black hole, so you will have it can have a capture cross-section that is similar to that of a black hole. So for example, so here I chose to present something that looks very different. But if you look at the images that are in this paper by Saurabh and collaborators of 2026, actually you get something that is a very good mimicker of a black hole.
Can you have photon rings?
Yes, I mean, they can have photon rings.
And it's here in the image was really thin as it was out shadow.
Well, it is so because the exterior geometry is very similar to black holes. So well, for those cases in which the exterior geometry is very similar to black holes, it will be exactly the same as in the case of black holes. So how much percentage of the light that is in the photon ring, how much percentage of the light is in the photon ring will depend on the particular accretion disk model. But but this type of accretion disks so made of more or less coffee environments of optical in plasma will be more similar to the last examples that were shown in the lecture by Gonzalo Olmos.
My question concerns the Warhol case, and it's an exotic question for exotic cosmic objects. So you mentioned the effect of the accretion. Does it actually matter which universe the accretion happens? So if you have the accretion in the other universe, is there any difference?
Yes. Sorry, I moved the wrong direction. Actually, yes. So the appearance would be different if you look at one side or at the other side. So, unfortunately, in this paper, they still didn't provide GRD images, so they only perform the GRD simulation. However, well, you can see that there is some difference on one. This is on one side of the throat, and this is on the other side. So on one side, you can see some. So the exterior pan is very similar to typical black hole accretion simulation, except that the center is bright, no? Because matter is accumulating at the throat. But if you look at it from the other side, you can see this bright sphere where matter is accumulating, that is also the throat. But you will see winds that are coming out of the object. So indeed you will see something different from one side than from the other side. And this is just the journey, you know. So there can be many optical effects that are associated to work force. Here it is unlikely that we see this because probably we will just see the central darkness, but well, until there are no VRD images, it would be, we can speculate, no? It would be very interesting to see what one actually see.
That will make it to the newspaper headlines. We'll see.
Yes, but well, the only thing that we can say so far is that Sagittarius A** and 87 don't seem to be wormholes of this kind.
So thank you, Héctor, for your presentation. I have a quick question, actually. I'm wondering, because there are many works regarding the existence of black holes inside dark matter halos, so they model this kind of environment. And I'm questioning myself if the dark matter halo outside the black hole can modify the predictions of these accretion-based simulations, for example. Do you know if there is any work in this direction who says that there is no effect at all, or there is insignificant modifications in the simulations?
So that is a good question. I know that there are works that have calculated the size of the photon ring if the black hole is immersed in a dark matter halo, and the difference doesn't seem to be very noticeable. But I have not heard of works that consider the case of GRD simulation. But so I think that in general, I would not expect that there are a lot of changes, because when the dark matter halo is very big and very dilute, let's say. So unless you have a dark matter model that produces a lot of accumulation,
Like a spike near the horizon?
Exactly. If it produces a spike near the horizon, like in this Rubinia wedges Rueda model, then probably that would change the image, no? But I think most popular models probably would not make any difference.
I see. Thank you very much.
Or any more questions? Let's thank